Alright, so in this example we have a pulley system that's under a constant velocity, 2 meters a second. So when we pull down on A here, it's going to come down. It's going to pull all the way through all these pulleys up against the ceiling, which is going to move this pulley and our load E here, which is a mass. It's going to pull it up, right? So first thing we want to do is we want to choose a coordinate system. I always stick with kind of, the given thing that's how it's all laid out here. So I choose like Y as positive going up, X as positive going out to the right. So our velocity here will actually be a negative pulling down on A. The next thing we want to do is we want to choose what's called a datum, which is what we have indicated here with our line that comes across. Datum. So the idea with the datum is that the rope above the pulley is a constant length, right? Like that pulley doesn't, it's not going to change radius. And this, when we pull this pulley up, it's not going to be able to go any higher really than this length or this height here as well. So what we want to do is we want to add up all the length of all the ropes that's in here, and we're only going to count the stuff that's in between our datums. So there are two ropes. There's one over here, goes all the way through into the ceiling, and then there's this other rope here that comes through from pulley C and then goes all the way up to the ceiling. And so we're going to need two length equations to solve for that. So with the one on the left here, which we'll call L1, the total length that runs through these two pulleys, what we're going to have is the total length, L, and that's going to be equal to this length here, SA, which is going to get longer when we pull it, and plus 2, SC. So be this length and this length. So there's 1, 2. All right, nice and easy. On rope 2, the difficult thing is always kind of realizing that we have two lengths. We have this length here, this length, and we'll denote this big one here as SD. And what we want to find is we really want to find the length that this SC is gonna kind of like grow to. So it can't be any larger than SD, which is the one on the right. And it's going to be minus a little bit over here. So what we'll have is we'll have this whole length coming from here, SD minus SC. That's going to tell us how much rope we have. Now we have our two length equations. The next thing we're going to do is we're going to take the time derivative. So what we'll get is DL equals DS over DT plus 2SC. Now, the total length of rope doesn't change with time, so what we're going to have is a constant, which will be 0, right? If the total length doesn't change over time, it's constant, derivative, constant, 0. Over here we'll have ds, a plus over time derivative, and that's going to be that's actually the definition of velocity. So we'll have the total the total length or the total position, change in position over the change in time, which v velocity, right? That was our definition. So we we'll solve those for velocity. We get two equations, right? Two pieces of rope. And being very careful with our signs, we'll combine those equations. 2VC equals 2VD. And then we'll go ahead and put in our VA over here. So what we get is a final velocity of 0.5 meters per second. So when this is moving down 2 meters a second, this part over here, pulley D, which is attached to E, will be moving up at 0.5 meter a second.
Alright, so here for this second problem we have the same setup, same three pulleys, a mass, and the end of point A being in the same spot. The difference here is instead of a constant velocity at A, we're going to go with a force and determine the acceleration of mass E. Mass at the mass of E is 50 kilograms with a force of 150 newtons being pulled downward. Our coordinate system is standard set up with y up being in the positive direction and x to the right being positive direction. The tension in an ideal rope remains constant throughout this system. So here we have two systems. We have system 1, which is our first rope, and we have system 2, which is our second rope. So what we know is that 150 newtons is being pulled down, so that is the tension throughout this rope. So what we're going to do is the link between the two systems is pulley C, with the second rope being connected to it. So we're going to evaluate with a free body diagram the forces at C. So as you can see here, we have our two tensions, tension 1 both going upwards, and then we have tension 2 caused by the mass of E pulling down on the system. Once we apply the force equilibrium at pulley C, some of the forces in the y direction about C equals 0. We have our two tension 1s in the upward direction, and we have our tension 2 going downwards. Solving this equation for tension 2, which is what we're trying to find, we have 2T1 equals T2. Plug in our initial force condition, and we have T2 coming to 300 newtons. Once we know the unknown force of T2, we can evaluate at pulley D to find our forces here. So at pulley D, we have our two T2s and the weight of our mass. So to quickly solve for mass, it's just mass times gravity. So we have 50 times 9.81, which gives us a weight of 490.5 newtons. Now we apply our Newton's second law, the sum of the forces at pulley D in the y direction equals mass times acceleration. These forces sum to T2 plus T2 minus our weight, which is mass times gravity, equals mass times acceleration at E. To solve for A, which we have right here, we have 2T2 minus mg over m. Plugging in our knowns, T2 being 300, our weight, which we solved for earlier, and then our mass of 50 kilograms gives us an acceleration of 2.19 meters per second squared.